Okay, so this X test means test. This is the testing data set from which I have to compare my values. Okay, so it is like I know the picture, it is of a dog, but the computer says it's a cat. That means it is wrong, and I have to compare the true Y values. So this just remember Y values. Y means the target variable which I want to predict or which I want to measure, and X values are all the parameters based on which I want to predict the Y value. Okay, so for that example of students, the height and weight can be the X values and the marks are the Y values. Okay, and X test means the part of height and weights which belong to the test data set. Test that split that we do, the test part of the data set. Okay, so let's go to the next slide. Okay, so basically like we have a trade model which so this example is related to that cat and dog classification example. So our trained model which I trained on 100 images, I showed 100 images to my computer and gave it some time to train on that. I gave the answers also. Okay, this first image is of cat, second image is of dog, third image is of dog, fourth image is of dog, fifth image is of cat. So I gave the labels and those 100 examples and asked like and trained the model. Okay, so next, now I'm testing. My model is done. Now I'm testing how my model is performing. So I gave this image, test image from X test. That means like it is just an image from this part. This is the name of the testing data set. So my images suppose have 120 images. So I divided 20 images for the test data set and 100 images for the training data set. On those 100 images, I have made this model, and on this 20 images, I am doing the testing. Yes. Okay, these are used here. So I gave this image and I see the output. So the output says that this is the correct label. This is the label I know, right? That this is a dog. But my computer's prediction says dog. That means the this dog, like the output of my model is dog, and the actual value of the output is also dog. That means it is a correct prediction. Okay, so I need to compare the output value and the actual value to check the error. So here is no error, it is a correct prediction. Suppose one more, I showed another picture and the model says cat, but it is actually a dog. So this is wrong, because these when I compare I get an error. So I will say it is a wrong prediction, right? So for like I'm checking this on 20 such images. So how can I club this information together in terms of, so for these many pictures the prediction was wrong, for these many pictures the prediction was correct, for these many dog pictures the model said they were cat, for these many cat pictures the model said these were dogs. Okay, so there are some kind of matrix or some kind of numbers, important numbers that I can look at for a model to check its performance. Okay, so we repeat this exercise for all the images in the test data set. So for our example, we repeat this exercise for all the 20 images in our testing data set. And at the end, we will have a count of the correct matches and a count of the incorrect matches. Okay, these were the wrong and these were the correct answers. Okay, normally like we do in our exams. Okay, so the key realization we need to make is like in the real world, not all the
Right.
incorrect or the correct matches hold equal value. Okay, so this line, this sentence like makes a, you need to keep a note. So in the real world, not all the incorrect or the correct matches hold equal value. Okay, so you can think of it as like suppose you go for a corona test. So your the output of the test can be whether you have corona or you don't have corona, right? So this is the two output of the test. But in reality, you there are two options. Either you have corona or you don't have corona, right? So if you have corona and you got tested, like yes, your test is yes, you have corona, then of course like it did the right thing. It is important for you to admit to a hospital and get the proper medication. But if you don't have corona and the result showed you have corona, then it is a very big problem, because this may cost you your life. Like you will be hospitalized for no reason, and like maybe you can get some disease there. So that is what this sentence means. In the real world, not all incorrect or correct matches hold equal values. Okay. So like also in the real world, a single metric won't tell the complete story. Single metric means a single measure of the error. Like I made a model which can predict whether the person is male or female just by seeing the picture. And you say, okay, what is the accuracy of the model? The model is predicting 80% of the times correctly. Okay, so it can be one thing that okay, for 80% of the time it will say correct, right? Like your the prediction is correct, but it is not complete. It does not tell you how many times it is giving the answer as a male for a female photo and female for a male photo, and what is the data set you have trained, right? I'll give you an example for this. Okay, so to understand all of this, let's bring back the four matrices that we mentioned and how they are calculated. These four matrices are accuracy, precision, recall, and F1 score. So so we like organize all of this information in a confusion matrix, which we will see at the towards the end of the class. It is very important, and like this is the only thing that we'll be using in all of the machine learning evaluation for the evaluation of all the machine learning process that we do, right? So accuracy is the in any classification problem is the number of correct predictions made by the model divided by the total number of predictions. Okay, simple. Number of correct answer divided by total number of answer is your accuracy. Simple, right? So if your model said correctly predicted 80%, 80 times out of 100, then your accuracy is 80 by 100, right? So for example, if the X test set was 100 images and our model correctly predicted 80 images, then we have 80 by 100, 80% accuracy, right? Simple. Accuracy is useful when the target class are well balanced. This is the term, well balanced, and you will know why. In our example, we would have roughly the same amount of cat images as we have the dog images. Okay, so suppose think of an example of the same example, cat and dog. I have to classify. I have to make a model which will classify whether the shown photo is of a cat or a dog. Okay, now I am training my data based on the 100 images, and I'm testing my data on 20 images, right? So 20 images will never model will have never seen those 20 images before, but it has seen those 100 images while training multiple times, right? So suppose now what is contained in those 100 images is very important. So what is the data that I'm used for training the model is very important. Okay, so if I tell you 2 into 2, if like you were taught 2 into 2 is 10, then for in your whole life you are being taught the same thing, 2 into 2 is 10, then you will only teach this to others, or you then this will be your whole uh, so your whenever anybody asks you what is 2 into 2, you will say 10 only. Why? Because the data which was used to train you was wrong. Okay. So similarly, suppose for those 100 images, there are 99 images of dog and only one image of cat. Okay. Right. So I am showing 99 images of the dogs and to my computer and only one image of cat. Right. So what will be the output? So what you can think of the model in such a case? Suppose
Dog.
I have like so for such kind of a model, the computer can make a simple model. Whatever may be the input, you just output dog. Okay, because he has seen 99 images of dog and only one image of cat. So he can simplify the model to be whatever image they show me, I should set dog, just dog. Keep printing output dog. So there is no machine learning. Simple. Whatever is the input, you keep the output as dog, right? The output is dog. Now I'm testing these images on 20 dog images. So what will be the accuracy of my model? 100%. Because my model is only trained on dog images. 99 dog images he has seen my model, and I'm testing this on 20 dog images. So my model accuracy is 100%. It will never be wrong. Now suppose I'm testing it on 20 cat images. What is the accuracy of my model? I'm testing it on 20 cat images. 0%. My model is absolutely wrong. Now suppose if I'm testing it on 10 dog images and 10 cat images, so my model accuracy will be 50 or 60%, right? Because the model has never seen a cat image before, right? So accuracy is not a good choice with unbalanced classes. So this is what we mean by unbalancing or using balanced classes. So your data that you are using for training the model should be balanced. That means if you are using 50 images of dog, then you should use 50 images of cat. Then only it will be properly balanced. Okay. Imagine we have 99 images of dogs and 1 image of cat. So our model was simply a line that always predicted dog. You would get 99% accuracy. The same thing. Okay. So imagine we had 99% of dog and 1 image of cat. Our model was simply a line which predicted dog. So like the model will be just give an answer dog irrespective of the picture. So in this situation, we want to understand what is recall and precision, right? For such a case, if our data, because we never know what kind of data we may find, that's why just using accuracy is not good. We should use recall and precision for such a case. Now we will understand what is recall and what is precision. So recall is the
Vinay, I have a question.
Yes.
If the data is unbalanced, how to handle that? See, suppose when you have 70 dog images, and you have 30 cat images, how to handle that?
So you have this data like 70 dog images and 30 cat images. Then either you collect more cat images or just train your data on 30 and 30 dog and 30 cat images, because you can handle training
that
data.
I can't choose, right? Because I'll be taking randomly, right? Data usually will be taking randomly.
So that random you are the guy who is building the model. So it's in your hand, like whether you do random sampling. If you know that my data is the classes are well balanced, then only you will take random sampling. Otherwise, you will select
manually. I'll agree with you. Suppose if the labels are more, see for example, if you go to ImageNet, there will be around 500,000 images will be there, right?
Yes.
1,000 classes will be there, or 5,000 classes will be there.
5,000 classes.
It's not possible. Classes.
5,000 classes. What are you saying?
Labels.
Labels. But labels can be 5,000, but there are only two types. No, either they will be cat or they will be dog. Okay.
I'm talking about we have different like cat, dog, or we have
so
bird,
like for whole country, let's take an example of all the cats and dog of India, right? You are saying how to handle that, right?
No. My thing is I have different classes, like see, you take on only dog and cat. So I'll add birds, I'll add some door, computer, like that I'll add.
Yes. Okay.
If I add like that,
so you want to do any random object detection? Any object you should be able to detect. Table lamp, table, chair, car.
Yeah.
Yes. So for
at that time,
yes. So your question is, so how to handle such big data?
Yeah, such big data, and thing is that one data will have, for example, dog will have more number of images in the training data. The others will be lesser.
Okay.
Yeah.
So what you can do is, like, one thing is simply you take equal number of proportions. Okay. Equal number of samples from each class.
Right. Equal number of samples from each class.
Yes.
Okay.
But suppose
so this was a question which is asked in the interview for me.
So you can take so you need to look at the distribution of the classes. Okay. Suppose in one of the classes one of the classes is like lions, elephants, kangaroos. Okay. So if you look at if the data set in question or in analysis is India's demographic, or it is an Indian data set, then we can say that yes, obviously number of dogs will be more than number of elephants, and it will be more than number of lions. So we can take proportional samples. Okay. So suppose like there will be multiple cars. So we can make an estimate of like what is the proportion of all the classes in this target variable. Okay. So suppose I want to identify all the animals. So I can make an estimation based on like the domain knowledge. I can consult some previous data set. I can consult some publication which can say, okay, so out of all the animals, 40% are dogs, 30% are cats, 10% are those you can say general wild animals, 2% are lions, 3% are elephants, 5% are kangaroos. So I can take samples from each class proportional to their estimated population. Okay. I can do stratified sampling, just like we saw in that example, right?
So you have to go with it's just like a slam sampling, right? So you have to take
Yes.
samples from each particular classes,
Class.
and you need
Yes.
to train it, and we need to test it later.
Yes. And we need to take
Okay,
into
Vinay.
consideration, like we need to take samples proportional to the actual population of the class. Okay.
Okay. We have to take
So
proportions.
yeah,
Okay.
because we can think like that, because number of cats and dogs are almost equal in, we can take them as equal. Then I will taking 50% dogs, 50% cats. Now if I want to compare cat, dog and lion, then obviously like the population of lion is proportionally less, and we are making a data set for maybe this wildlife sanctuary. So they will be observed, they will be putting cameras in jungles in, and then those national parks, and to count, to recognize whether it is a dog, it is a cat, or it is a lion. Then I will take samples proportional to the actual population of my classes. Okay.
Okay,
Are you
Vinay,
getting?
got it, Vinay.
Yeah.
Yes, Vinay, got it.
Okay.
Yeah.
Okay. Cool.
Thank you. Yeah.
So recall is the ability of a model to find all the relevant cases within a data set. Okay. So mathematically, it is number of true positives divided by the number of true positives plus number of false negatives. Okay. So basically, recall is how many dogs my model was able to identify, divided by total number of dogs. Okay, simple. So I want my for the class dog, the recall is my model was able to correctly identify 80 dogs out of 85 dogs. Okay, so recall will be 80 upon 85. Okay, so this concept of true positives, trend true false negatives will become clear later on in the slides, right? So precision is the ability of a classification to identify only the relevant data points, defined as the number of true positives divided by the number of true positives plus the number of false positives. Okay, it is precision means like of all the identify classes, how many of them were identified. So like for this, you need to understand, I need to explain this true positive and true negatives, right? So we will look at after like some few slides. It is like wrongly placed. So recall and precision. So often you have, so there is a trade-off between recall and precision. While recall expresses the ability to find all relevant instances in a data set, precision expresses the proportion of the data points our model says were relevant, actually were relevant. Okay, so maybe we can jump to that slide. Yes. Okay. So we are jumping to this slide. We'll go back to the previous slides also. Right. So this is what a confusion matrix looks like. Right. So on like top or on my columns, so it is a 2x2 column. Right. Like this. So on column names, columns are, we have predicted condition. Right. So whether it is prediction can be positive, prediction can be negative, or simply it can be a dog or it can be a cat. Simple. Positive, negative are just two classes. It is for a binary classification, right? These are the predictions. So I'm predicting like this is a dog, and my prediction says it is a cat. It is on the rows we have actual condition. So actual condition says it is a dog, actually a dog, and it is actually a cat, right? So true positives are, my model says yes, it is a dog, and in actuality it is also a dog. So dog, dog, right? My prediction says. False negatives are, my prediction says it is a cat, but in reality, in reality, it is a dog, right? So, and similarly, false positive is falsely predicting positive, right? You can read this thing as falsely predicting positive. Positive means any one class. So, like my prediction says it is a dog, but in actuality, it is a cat, right? And true negatives are like truly predicting negative, means like they belong to the second class. So my model says it's a cat, and in actuality it is also a cat. So these things, these can be the four possibilities in a classification problem, right? My model says it's a dog, it can be actually dog. That means like, so this is a desirable case, and this is a desirable case, but this case and this case is an error. it is wrong classification. So these are called type 1 and type 2 errors. Like it is important, we saw that in statistics course also. So falsely predicting so if a man goes for a pregnancy test and he comes out to be positive, then it is a false positive, right? Because I'm falsely predicting that a man is positive, but in actuality he cannot be negative. Biologically a man cannot get pregnant. Okay, so it's a false positive or type 1 error. It is called type 1 error. And when a pregnant woman goes for a pregnancy test and the report comes negative, that means my test says the woman is not pregnant, but in actuality the lady is pregnant. That means it's a false negative. So the trick to remember these two errors are really important. Let me resolve the ink and again take the pen. So these two errors are really important, and so all of our classes, all of our model revolves around these two errors. Okay, so false positive, to remember, false positive is falsely predicting positive when in actually the data point is negative. Okay, false positive means falsely predicting positive. False negative is falsely predicting negative when in actuality it is positive. So for a cat and dog, suppose this is my dog class, okay, and this is my cat class, right? And for positive it is dog, it is cat. So false negative is my model says it's a cat, but in actuality it is a dog, so it's a false negative. And false positive will be when my model says it's a dog, but in actuality it is a cat, right? So here positive negative corresponds to two classes, right? The two values a class can take, whether it's a male or female. So if the positive, I can assign positive to male or negative to female. So this convention of positive negative is taken from diagnostic testing. Okay, whether you go for corona test, so corona test comes positive or negative, HIV test comes positive or negative. Okay, so your SARS, Ebola. So for all of these tests that we go for, so this confusion matrix table is taken from this diagnostics, or this, you can say, medical background. So that's why we are using these terms positive and negative. So basically they are just two terms, two possibilities of an outcome. Okay, so whether it can be a male or female, and so on the columns I have the predictions by the model, on the rows I have in actuality what they are, right? So this thing will become really clear here now. So I have all the things right here. So these are all the matrices that we can use, right? So we were talking about accuracy, right? So accuracy is total predictions, total correct predictions divided by total number of predictions. So my total correct predictions are, this is correct prediction. So my computer says it's a dog, and in my model says it's a dog, in actuality it is a dog. My model says it's a cat, my computer says in actuality it is a cat. So these two are correct predictions. And what are total number of predictions? This plus this plus this plus this, right? Total predictions are this many. So accuracy is this one. TP means total positive plus total negative upon total population. Total population is sum of all four, right? So this is accuracy. Now we will look at precision, right? So precision for dogs will be true positives upon predicted positive, right? So suppose let me clear this all and make an example, right? It is all ink, right? So in total population, so we had 120 dogs. Out of them 100 were used for test training, and 20 were used for, suppose 20 were used for testing. Okay, so true positive, let's take an example. Out of those 20, 10 were dogs. So 10 were dogs, 10 dogs, and 10 were cats, right? This is actually the condition, but my model says there are 8 dogs and 2 false positives, and here it says maybe 6, and 6 will be fine, 4, right? So this is the distribution of my model, right? So now I want to figure out what is the accuracy of my model. So accuracy of my model is like correct prediction. So like for 8 dogs, the model correctly predicted they are dogs, and in actuality they are dogs. For 4 cats, the model actually predicted there are 4 cats, and they were actually cats. So my accuracy is 8 plus 4, 12 divided by 20. Total case is 20, right? 8 plus 2 plus 6 plus 4, right?
60%.
60%. So now I look at precision. So precision is for total positives upon the total predicted positive, right? So precision is how many times my model correctly predicted dogs. So it correctly predicted dogs 8 times out of how many times my model said like this is dog, right? So it will add this plus this, false positive and true positive, 14. So in 14 times my model said this is a dog, this is a dog, this is a dog, but only 8 times it was actually a dog. So this is your precision. Okay, getting, so precision will be for a class. So for dogs the precision is 8 by 14. For cats the precision is 4 by 6, because this is the correct prediction of a cat, and total prediction of cat was 2 plus 4, right? You can also like refer to this as false omission rate, same thing. It is the formula are explained in the form of this, like positive negative and positive negative combination. So precision is how many times my model correctly predicts a class divided by the total number of that prediction, like how many times it predicts for the class. Simply my model says correctly predicts 8 times like this is a dog, but how many times it totally said that they were there, this is a dog, this is a dog? It was 14. Okay, so my model, so like there are two things. One thing is the actual distribution. So actually there are 10 dogs and 10 cats, but according to my model there are 14 dogs and 6 cats, right? If you add them, so this is the positive prediction. This is a positive prediction, means how many times a model predicted it's a dog. So you will add this and add this. So 14 times my model said there is a dog in the picture. Okay, but 6 times my model said there is a cat in the picture, right? So there is some error. How can I evaluate that? So I can take precision like this. Then what is the recall, right? So recall is total positive. So recall is same like how many times the model correctly predicted that there was a dog, this is a dog, so it is 8. And how many dogs were there actually in the data set? There are 10, right? Sum of this row. So sensitivity or recall, they are or true positive rate, there are different terms for the same metric. Okay, so recall means like you want to recall something from a memory. So like in actuality there were 10 dogs, how many times my model was able to tell like, okay, this is a dog, so it was 8 by 10, so like 8 by actual number of dogs. And precision is okay, so there are how many times a model said this is a dog, this is a dog, but how many of them were actually dogs? Okay, so 8 by 14, right? So it is something like my model is saying, okay, there are this many dogs, there are this much, there are these many dogs multiple times. So these two things will tell me something about my model. So my model is predicting number of dogs more wrongly, right? It is like giving this is a dog, but in actuality there are lesser number of dogs in the picture. That means there can be some problem with the training set, right? Maybe he has seen more number of, so like if this is the data 8264, then probably the data set on which my model was trained has more pictures of dogs, because it is making prediction of 14 for dogs and 6 for cats. And if you see the precision of cats will be a number of 4 by 6, that is almost 66%, right? 2 by 3. And if you see the recall for cats, it is 4 by 10, 40%. That means my model is not able to classify cats properly, right? So this is what confusion matrix is, right? So you can look at, so there are like all different kind of terms. So based on the domain knowledge, or based on the case, based on the data that we are referring to, we can we may want to report any of these, right? Suppose most of the time most common is precision, accuracy and recall, but other times you can use other terms also to know. So whenever you read a paper or whenever you read a report, you will be using all these kind of terms. So you can refer to this table all the time, right? So now we just go back. Now we have like what is recall and precision. So we have to choose which one to. So for a case like coronavirus. So for coronavirus, you can tell. Can you tell me like which is more important? False positive we should avoid or false negative we should avoid? So false negative is falsely predicting that you don't have corona when you actually
False
have
negative.
corona. And false positive is
Okay.
when you actually have falsely predicting that you have corona when you don't have corona. So
Both.
we have to decrease both, but there is a limit. So currently, like your previous answer was correct. We want to reduce false negatives. Okay, so that's why in our model we want, okay, so if I'm testing 100 people, if like 40 of them are actually corona positive and 20 of them are like false positive, it is okay, right? But if even one case goes into false negative, then that's a huge problem, right? You think you take the situation as your neighbor goes to corona test and and the test comes negative, but he is actually having corona, then such a case is very serious. It can affect lots and lots of people. Okay, so for medical testing, depending upon the kind of disease that we want to test, we design test like this. We should have what do you want to increase, like what can we avoid? Do we want to avoid false positive or do we want to avoid false negative? Okay, for corona it is fine. For corona we want to avoid false negatives. Okay, like I don't want even one guy who has corona to go as negative test result. Okay, I can have 20 people with who do not have corona, but the test report says they have corona. It's fine, they will get better anyhow. But I cannot leave any single one person who has corona and the test report says a negative, right? And if the case was something different, suppose you say for cancer treatment, for that's why we for cancer treatment you will not get positive result in just one go. You must have heard some stories, maybe your relatives or like any other friends, like he went to like four doctors before he found that he has cancer. Why? Because in cancers we want to reduce false positives, right? We want to reduce. So if we get tested for corona, there is a very less probability that we will get positive result even we have corona. I'm sorry, even we have cancer. This is done because in order to avoid unnecessary uh, burden to the burden to the patient. Okay, suppose we went to for this checkup, cancer checkup, and just like corona, every second person is tested for lung cancer because he was coughing. So he has to go for all the chemotherapy, all those like costly tests, right? So it is wrong on the part of our government or the testing agency to unnecessarily ask people to send so much of money, because the consecutive tests of cancer are very costly, very costly. That's why to reduce unnecessary burden on the patients, they are reducing the number of false positives, not false negatives, right? So like you may have to do multiple testing to actually get, okay, yes, you actually have cancer. Okay, because like every day you cough and you go to a doctor and he did a cancer test and it comes out you have lung cancer, but you did not have lung cancer, that you only know after going to subsequent rounds of diagnostics, right? So with this table, right, and we have this F1 score as the third metric, which is the harmonic mean of precision and recall. Okay, so it is like F1 is equal to 1/1 plus precision, 1 plus 1 upon recall, right? So why they are taking a combination of both of these, because they want to punish the extreme values, right? So suppose there is a classifier with a precision of 1 and a recall of 0, right? So recall is 0 but precision is 1. So the average, if you take the average of precision and recall, it will be 0.5, right? But the F1 score will be 0. So you want to get a combination of both of these to a certain level, like precision should be good and recall shall also be good, right? So that's why we take F1 score, right? Suppose your precision is 1. Precision is 1 meaning you are able to predict 10 dogs out of 10 dogs, right? But your recall is 0. right? So your precision is, you want to say like these, I predicted 8 dogs and total dogs are also 8. That means you predicted 8 times, right? You predicted 8 times that there are dogs. 8 out of 8 times you were correct, but your recall is 0. Recall is 0 means your recall is total number of true positives upon condition positives, right? So your when your recall is 0, like you are so like for that means for one class you are able to make 100% corrections, but for the other class your prediction is 0. So your classifier is wrong, right? So where my model is actually able to predict dog every time, but but for when it comes to cats it is 0. So I don't want a model like this, right? So if I want to take, suppose someone tells me, okay, when the precision is 0 and recall precision is 1, recall is 0, you take the average, right? And you take the average and use that as your metric. But that will be wrong. But that model is absolutely wrong, right? So I have to use F1 score, because F1 for when the precision is 0 or recall is 0, the F1 score will be 0. So it is penalizing these extreme cases. Okay, so just keep in mind this confusion matrix. It will be asked in like all of your interviews, all of your machine learning interviews. What is this? What do you mean by confusion matrix? How do you evaluate a classification problem? Okay.
Only 2 minutes.
Yes, yes, yes. So like guys, I have a class from 7:30, so maybe we have to stop
Okay,
here.
we'll continue
We have
to, yeah, yeah.
nothing. Yeah, we do not have much left. So just regression example. Yeah. So we will look at this evaluating performance of a regression for tomorrow, right?
Okay.
Okay, guys, and I'll share this PPT today so that you can go through it once.
Okay.
Okay,
Okay.
guys, thank you for
Thank
your
you.
time.
Bye bye.
Take care.
Bye
Bye-bye.
all.
Thank you.
Thank you, sir.
Bye.
Bye.